Hello students, I am Professor Ambika Devi, Assistant Professor of Physics, Government First Grade College, Bidar. Today's video is related to Session 31 of BSc 5th Sem, Solid State Physics course, which is prescribed in the colleges affiliated to Karnataka State, Gulbarga University, Kalburgi. So let us now begin with the session 31 of the BSc 5th Sem Solid State Physics course, and this session is related to Weiss theory of paramagnetism. Students, today we are going to discuss about Weiss theory of ferromagnetism. Ferromagnetic materials are those materials which are strongly magnetized along the same direction of the applied strong magnetic field. Means student, ferromagnetic materials are those materials which shows strong magnetic properties. This theory of ferromagnetic material was given by the scientist Weiss in 1907. Weiss modified paramagnetic theory. Weiss modified paramagnetic theory and explained as ferromagnetic theory. See students, now question arises that on what basis Weiss modified paramagnetic theory to ferromagnetic theory. So, according to the concept of molecular field, or on the basis of concept of molecular field, he modified paramagnetic theory and explained as ferromagnetic theory. Means students, means introduced domain concept. In case of domain theory, in between the atoms of the material, some special interaction is to be takes place. Because of this interaction, all atomic magnets align in a one particular direction and they form a group called, these groups are named as domain. Okay. So, according to Weiss, the atomic magnets of a ferromagnetic substance are grouped into certain regions, and these regions are named as domains. Okay. When the substance is in the unmagnetized condition, what happens? These domains form closed chains with no free poles. But when the substance is in magnetized condition, what happens? These chains break up and the domains gradually set themselves with their magnetic axis, all pointing in the field direction. Thus, ferromagnetism is a crystal phenomena. Okay. Now, Weiss assumed that a molecular magnetic field exists at the position of every atoms or molecules. This field, applied field, arises due to the interaction of all neighboring molecules. The molecular field, this molecular field is proportional to intensity of magnetization. Here, the molecular field is represented by beta I, and this beta I is directly proportional to magnetization vector I. This I is the intensity of magnetization. Now, here Bi is directly proportional to I, and this expression is written like this: Bi equal to beta I. Here beta be the proportionality constant, and this proportionality constant is also called as molecular field coefficient. Okay, the effective field strength beta E. This effective field strength beta E is also expressed as vector sum of the external applied field strength B and the internal molecular field strength Bi. See here, this is the effective field strength, which is equal to sum of B plus Bi, where B be the external applied field strength and Bi be the internal molecular field strength. Then this above equation becomes Be is equal to B plus beta I. In place of Bi, we are substituting beta I. Students, here we are considering 1 gram mole of the substance. Then intensity of magnetization I is equal to sigma divided by m by rho, and saturated value of intensity of magnetization is equal to sigma naught divided by m by rho. Okay, see, the domains will obey the general theory of paramagnetism by Langevin. According to the Langevin theory, I by Is, intensity of magnetization, ratio of intensity of magnetization to the saturated value of intensity of magnetization is equal to sigma by sigma naught, where this sigma is gram molecular magnetic moment and sigma naught be the saturation value of gram molecular magnetic moment. I already told you, no, this domain will obey the general theory of paramagnetism, which was given by Langevin. According to that theory, I by Is equal to sigma by sigma naught, which is equal to cot alpha minus 1 by alpha. See a student, alpha is defined as mu Be divided by Kt, but we know that Be is equal to vector sum of B plus beta I. So here we are substituting in place of Be B plus beta I. So alpha equal to mu into B plus beta I divided by Kt, where mu is dipole moment of individual atom, K be the Boltzmann constant, and T be the absolute temperature of the substance. Okay, when external field is 0, when external field becomes 0, means this B is equal to 0, then what happens? B is equal to beta I. Okay, but we know that B is equal to B plus beta I, but here B becomes 0. When the external field is 0, then B is equal to beta I. Beta as it is. In place of I, we are substituting sigma rho divided by m. After substituting all these values in alpha, alpha becomes alpha is equal to mu beta sigma naught rho divided by RTM. Okay, here R is the n into K, where n is the Avogadro number. Lastly, it is expressed as sigma by sigma naught equal to RTM divided by sigma naught square beta rho into alpha. Okay, then see this figure. This figure shows a graph between magnetization and alpha in the above equation, in equation 3 and equation 4. See here, equation 3 and equation 4 simultaneously determine the condition of spontaneous magnetization. Okay, equation 3 in the above equations, equation 3 and equation 4 simultaneously determine the condition of which one? Spontaneous magnetization. This figure, see, this figure shows a graph between magnetization 2 and alpha, corresponding to which equations? Equation 3 and equation 4. See here, this curve is Langevin curve, this curve. This curve is Langevin curve corresponding to equation 3, while the straight lines are corresponding to equation 4. This curve represents the equation 3, straight line represents the equation 4, where the curve meet the line, where the curve meet the line. At this point, right, the solution sigma by sigma naught is equal to 0. This condition is not true at this point. Hence, sigma by sigma naught is equal to 80 is the true solution. This point represents this point represents the stable state of the spontaneous magnetization. Okay. Then next is, we know that see, this slope of the tangent at the origin of the Langevin curve, that value is equal to 1 by 3. So in last expression, sigma by sigma naught is equal to some constant into alpha. Already we derived that equation, sigma by sigma naught equal to alpha, which is equal to 1 by 3, since sigma by sigma naught is equal to alpha by 3, where alpha is here, alpha is a small value. Hence, the condition for stable spontaneous magnetization is given by mu beta sigma naught rho divided by RTM. That value is equal to 1 by 3. That in that last expression, the whole value is replaced by 1 by 3. So sigma by sigma naught is equal to alpha by 3, and this value is equal to T. If here T is less than this value, okay, this value is represented by theta. So here T is less than theta. At the Curie point, T is less than theta. Hence, below the Curie point, in the absence of the electric field, the domains are spontaneously magnetized to a degree depending upon the temperature. So, approaching the saturation values as the temperature approaches absolute zero. But above the Curie point, what happens? Above the Curie point, theta, spontaneous magnetization no longer occurs. The ferromagnetic properties disappears and the substance becomes paramagnetic. Therefore, Curie temperature is the transition temperature. Above the Curie point, the substance obeys Curie-Wien's law. This is about Wien's theory of ferromagnetism. In next slide, we are discussing about drawbacks of Wien's theory. See here, this theory fails to explain how internal field between the molecules of the paramagnetic materials possesses such larger values. Means how internal field between the atoms or the molecules arises. Okay. Why? And one more drawback is it fails to explain why the linear relationship expressed by Curie-Wien's law that breaks near the Curie